Hey everybody, welcome back. So in part one, we talked about reliability statistics and how to calculate scale scores and look for Chromebox alpha and all those fun things. In part two, we're actually going to get into the MLM piece of this, which is running some multi-level models. And just a reminder, we're using the LQ 2002 data set, which is the same one that's available from Garson. And we're primarily interested in this outcome, which I'll scroll up to the histogram, which is hostility. So we're interested in predictors of hostility, which is when a soldier is sort of hostile to the overall mission of that they've been assigned. And we're interested primarily in the relationship between hostility and our predictor of interest, which is task significance. So how important each individual feels that their job is. And we're also interested, maybe sort of in like a moderating context, in leadership climate. So does the individual's perception or the group level perception of leadership climate have an impact on hostility? So again, I'm working through this R Markdown file. Our go-to for multi-level modeling is the LME4 package, which is a very nice package for multi-level modeling. The first thing I've done here is I've created this empty list just called models, and I can come back to this later. We actually don't use it until the very, very end, which is where we will sort of combine things together. You know what, actually we don't necessarily need to do that. Sorry, I'm rethinking this on the fly, always a dangerous thing to do. But we can leave it the way it is, and that'll be just fine. Okay, so the first thing we want to do is run a null model for our outcome, which is hostile. And to do that, we learned about how to do this last week. So we always want to give our models a name so they become objects, and we can come back to them later. So I'm going to call this model.0 because it's the first model I need to run before I get to the substantive stuff. And that is going to be defined as an Elmer model, linear mixed effect regression. Hostile is my outcome. The tilde is sort of the equal sign, right? It's the other side of the equation. And then the only predictor I have is my clustering variable, which is company ID. So this is the syntax for defining that. I have in parentheses the number 1, which denotes that this is an intercept, and then the pipe operator straight up and down, and then comp ID, which is the name of the clustering variable. Okay, so I also have a restricted maximum likelihood equal to false here because we're going to be comparing models. If you're doing model comparison, it's actually better to use maximum likelihood and not restricted maximum likelihood. So I'm going to leave that the way it was. That was the way it was last time. And I'm going to use this LQ 2002.1. I don't think for our purposes it would make a difference if we used LQ 2002 or 0.1. 0.1 just has that extra variable that I calculated. And then I'm going to get a summary in the next line, a summary of this particular model. So hopefully this is starting to look a little bit more familiar. Here is my equation. Here are some fit statistics, AIC and BIC, log likelihood, so on and so forth. I have information about my residuals, and then my random effects and my fixed effects. So at least for now, I'm going to note where I'm starting in terms of AIC and BIC. So at AIC, I'm at about 5889, and BIC, I'm at 5905. I don't have to be super exact here, but I want to get a sense. As I add predictors, those estimates should go down because that's how I measure whether or not my model has improved. I want AIC and BIC to drop as I introduce predictors. Okay, so here are my random effects. They always start with random effects in R. And so here we have a random intercept at the company ID level, and that has a variance of 0.05, 0.06. And then I have a random term at the individual level that's called residual, and that's equal to about 1. So because this total is right around 1, I can kind of start to guess what the ICC might be, but I can calculate it too. And then it's reminding me I have 2,000 individuals nested within 49 distinct companies. And then I get one fixed effect estimate, and that fixed effect here is the average hostility score across the entire sample after adjusting for soldiers nesting within companies. And so it's about 0.9, so it's about 1 is the average hostility score. And according to the standard error and the t-value here, this is going to be very, very significant. One thing to keep in mind, just in general, with predictors, again, R is a bit snobby with how it calculates things. So R assumes that you sort of know the p-values associated with the t distribution, which I know is not something you have to know. Again, R was originally made for statisticians, and so you don't always get p-values, and you typically don't get them with Elmer results. And so I'll show you how to get actual p-values if you want them. But one way to think about this is in terms of the cutoffs. So if this t statistic is at or above 2 or below -2, that is generally considered to be the 0.05 confidence level. So that is, so in other words, for an estimate to be significant, this value has to be above 2 or below -2. Otherwise, it's going to be borderline or non-significant. I believe the 0.01 cutoff is somewhere around 3, maybe 2.7. And the cutoff for a 0.001 is like maybe 3.5 or something like that. I might be way off on that, so I'll have to double check it. But anyway, if an estimate is 4 or 5 or above, you can be very confident that the estimate is statistically significant. If it's below 2, it's you can start to wonder, that's probably not going to end up being statistically significant. And I'll show you a way to get an exact p-value. The reasoning here is, for whatever reason, the folks that develop a lot of the packages for multi-level modeling in R don't like to calculate p-values for a lot of this stuff because they see it sometimes as not reliable. Simulation has shown that it's pretty reliable, that you can trust it. For example, in Stata and other packages, you do get p-values for everything, but it's just kind of the way it goes. So you get good at reading the significance levels for sure. Okay, so another thing to do after you run your null model is to calculate your ICC. So here's a quick and easy way to calculate an ICC. You can run that, and remember that's just plugging in the company level variance, which is 0.057, divided by the sum of the company level variance and the individual level variance. Okay, and the ICC here is 0.053, so that's right at about the threshold at which we would expect to need to use multi-level modeling. That means 5% of the variation in hostility scores is between companies, and 95% of the variation is within. So there's actually quite a bit of variability within each company in terms of hostility, which means there might be a lot to explain there with individual level predictors. But there also is some variability between as well. In addition to this, we can calculate a likelihood ratio test. And here again, see that lazy loading. I'm just communicating that this is the likelihood ratio test that comes from the Elmer test package. And the function is called RAN. This is exactly what we ran last week. So RAN for model.0. And we get 2 models. So one model, this is the model we just ran, the top one. The AIC is 5888.9. And then if we delete single term deletions, if we delete that random intercept, the AIC goes up by quite a bit, actually, by 57 points. which is not what we want. 57 points with a 1 degree of freedom gives us a very, very, very small p-value. So this is a p-value that shows you that it's important that we have included the random intercept in our model. Okay, that should hopefully be reasonably familiar. So now we're going to start adding predictors, getting into the fun stuff. So we're interested in task significance. So let's add in task significance. So I'm going to call this model.1. And it, again, the notation and everything is exactly the same. All I've done is I've added a predictor, tsig, plus my random effect at the company level, my random intercept. And then I get a summary. So I'm going to run this. There it goes. Here's my fit information. And look at that. AIC 5600, BIC 5600. I don't know exactly, but I know that AIC and BIC were like 58 or 5900 before. So that is a huge improvement. That's like a couple hundred points. Pretty much any reduction beyond a point or two is going to be statistically significant. And so that's really, really, really good. I've definitely found a good predictor here. Here are my random components. Here's company ID. And so that is the random intercept at the company level, and here's the random term at the individual level. Now you'll notice that these will, as you add predictors, these random components will go down slightly. And what that means is you're explaining previously unexplained variation, because that's really what these random effects represent. These random effects represent variation that is unexplained by the predictors in your model. And so I think company ID was like 0.05. It's now 0.02. So we've eaten up some of that variance. And the individual residual was over 1, and now it's below 1 at 0.91. So that's all good. That's what we want to do. You actually don't keep calculating ICCs. I get that question sometimes. Do I need to keep calculating an ICC? And the answer is no. The ICC is based on your first model, your null model. And after that, you want to explain a lot of that variation with predictors. And so your ICC may drop a little bit. It may go away completely if you explain all of the higher level variation, and that's all fine because you're essentially the models are doing what we want them to do, which is really good. The real fun stuff is down here under fixed effects. So here we have an estimate for our intercept. And this has gone up. It was 0.9, now it's 1.96, and we'll talk about that in a minute. And then here's tsig, and that is my measure of task significance, and it is negative. And based on its t-value, which is negative 15, it is highly significant. So again, anything above a t-statistic of 4 or 5, that's going to be significant at the 0.001 level. So very, very significant. And as is my intercept. Okay, so what does this mean? What this means is, as an individual perceives their task as more significant by 1 unit, and this is basically a Likert scale, so 1 unit, moving 1 unit up on that scale, they are predicted to have a hostility score that is 0.3 points lower, again on a Likert scale. So people who perceive their jobs as more important are less hostile to the overall mission of the group. That's a good thing, right? That's what we're looking for. So, you know, if you can communicate the importance of one's job to someone, that's going to help in terms of reducing potential hostility towards the mission. Okay, so we call that model 1. Now, what I'm modeling here, I'm showing you the process that I recommend for building a multi-level model. I don't recommend dumping everything in at once, because when you dump everything in at once, you really don't know how it all fits together. I recommend building things sequentially. So start with your predictor you're interested in, add in some additional predictors, add in interactions, add in level 2 covariates, but do it in steps. You want to include this stuff in steps if at all possible. So here's a model I'm calling model.2, and here I'm adding in the measure of leadership climate. So now I've got tsig plus leadership climate. And I get a summary of this model. Again, so notice my random components are getting a little bit smaller. AIC and BIC are getting smaller. They're down to 5,500. They were at 5,600. And here are my fixed effects. And all of these are, again, significant. They're all very large or very small. So leadership is, again, about T-sig was about 0.3, minus 0.3. It's now about minus 0.18. And my new variable leadership is about minus 0.35. So what does this mean? As I perceive my boss, right, my sort of ranking officer, as developing a more positive leadership climate, I'm less likely to be hostile. My hostility scores will go down. Just like if I perceive a task as important, my scores go down. So those are both good things. Something to keep in mind here, we are again controlling for all the other variables in the model. So when we estimate T-sig, that would be estimating T-sig for two people who have the same leadership scores, who think the same way about their boss. And in opposite, when I interpret leadership, that is after controlling for or comparing two people with the same task significance. That's the nature of control in multiple regression. Even in multi-level modeling, that rule still holds the same. Okay, you also get sort of a correlation between effects, which is kind of cool. I haven't done anything with that myself. I just think it's interesting to see how these different effects are correlated with one another. Okay, so now we can test let's think about this in terms of moderation. So we've looked at the main effect of leadership, the main effect of task significance. Those are both very significant. So now, what if leadership is actually a moderator of task significance? So if I perceive my leader as being more effective, maybe I have a different relationship between task significance and hostility. Or on the opposite, if I perceive my job as more significant, maybe that changes the relationship between how I feel about my leadership and hostility. Remember, in moderation analysis, we can't really separate those two things. So to indicate a interaction, we've talked about this in module 2, we use the colon. You can also use the asterisk. It doesn't make a big difference. So we have the main effect of T-sig. We have the main effect for leadership, and then we have the T-sig leadership interaction. Everything else stays the same. This is model.3. And down here, we get our results. Things look fairly similar. So now I'm seeing I didn't get a big jump there in AIC or BIC, right? I'm at 5539, 5573. Up above here, I was at 5540. So I went down maybe a point, and I was at 5568, and I went up. It's usually not a good sign. You usually want a consistent reduction in both. So we go down here to our fixed effects, and the one we really interpret, again, when you do moderation, the only variable you're interested in is the moderator. That's the thing you want to interpret. The other main effects are really not as interpretable in a moderator model. Here's that coefficient. It's positive, and man, it's close, 1.78. That is really close. So I might hold that one in the back of my mind. I'm going to show you in a moment how to compare statistically, because I probably need a p-value for that one. I want to know for sure whether or not I should include that interaction, because that one is pretty close. So let's hold that one in the back of our mind. Okay, so let's assume for now we're going to put that interaction to the side, and we're going to add a level 2 predictor. Now here's where things get really interesting. So now, in addition to task significance and leadership, we now have a group mean, group average measure of task significance. So not only am I measuring how an individual feels about their task, I'm looking at overall how a group feels about its tasks as an overall mean. So I'm comparing the individual in the group in a really interesting way. And that variable is already calculated in this data set. It's called GT-sig. I'm going to show you in later weeks how to actually calculate that in R. It's not very hard. But for our purposes here, this is the group mean of task significance. And I've added that into the model in the same place. You can put the last predictor. And this appears to have some impact. Our AIC has dropped, our BIC has dropped quite a bit, or a little bit. Here are our variance components. And notice, I know I get really excited about these numbers. Notice what happens to the random variance at the company level. It gets really, really small. It's now 0.009 because we've introduced a variable at the company level. And so that variable actually explains quite a bit of variability at the company level as well, which is pretty neat. And sure enough, looking down here, it is significant. And it is equal to minus 0.27. So we have, not only do we know that the individual task significance is important, and that's over here, minus 0.17. So every 1 unit increase in task significance predicts a minus 0.17 decrease in hostility. We know leadership is important, and it's about 0.3 reduction. And now we know that the task significance of the group is also important. 1 unit increase in the significance at the group level predicts a decrease in 0.27 in hostility at the individual level. That's the wild thing. So what this is looking at is literally the impact of the group on an individual outcome. So not only am I influenced by how I feel about something, I'm also influenced by how others feel about it. And this is also statistically significant. It's at negative 3.3, so that's probably in the 0.01 to 0.001 range. These other two estimates are highly significant. But all three of these are going to be statistically significant if we calculate a p-value for those. So we've got something going on at the group level as well as the individual. And then in model 5, I add one more group level predictor, which is G lead. Okay, so we know that task significance matters at the company level. Does leadership perception matter? So I add that G lead variable in there, run it. And it looks like it doesn't, which is interesting. So G lead, the test statistic here is only minus 0.6. So remember, it's got to be either below -2 or above +2 to be statistically significant. So these three, T-sig, lead, and GT-sig, are still significant, but G-lead is not. So at the group level, at the individual level, it matters how you feel about your leader and how you feel about your task, right? But at the group level, it matters how people feel about the task, but it matters less in general how your group feels about the leader, which is kind of interesting. Those group and individual dynamics are sort of at play with one another in interesting ways. Okay, just a couple things I want to show you, and then we're finished. So remember back 2 or 3 models ago when I tried that interaction? And the interaction is called, I believe it was model.3. Yeah, here it is. So model.3 tested an interaction between task significance and leadership. To get a p-value for that thing, I actually need to compare this model, model.3, to a model that includes everything but that interaction. And that is model.2. And this is another reason it's handy to sort of build these things out in steps, because you can do these statistical comparisons between individual models. The only difference between model.2 and model.3 is that interaction. And so when I do a likelihood ratio test for those 2 models, that difference is due entirely to the significance of that added interaction term. So this works with any 2 pair of what we call nested models. A nested model is a model that includes all variables from a main model minus one. So you take one variable out. Those are called nested models. So to compare them, I can use this ANOVA function to compare model.2 and model.3. And this is pretty cool. It's just taking the fit statistics from one, and it even tells you what they are. So here's model.2. Here's model.3 with my interaction. Model.2 has an AIC of this and this. Model.3 has an AIC and BIC of this and this. This is the difference. It's about 3 chi-square points. And here's the p-value. So that p-value, because the only thing that differed between those two models was the interaction term, this is the p-value for the interaction, which is pretty cool. So the p-value is actually 0.07. So I would say that is borderline, but probably not significant. So that is the technique. Because R doesn't give you those p-values for every coefficient, you kind of have to be a little savvy and you have to compare nested models to see if the differences might be significant. Kind of tricky. Okay, so last but not least, I want to show you a couple tips and tricks for cleaning up these estimates. Now, these estimates actually aren't too bad, right? The formatting isn't too terrible. They're pretty easy to interpret. But the one issue is we've run 6 different models, model 0 through model 5. And it would be nice to put all these things in a table. And oh my gosh, the amount of time I've spent taking models like this and putting in tables. I want to show you some tricks for making that a little bit easier. So I showed you Stargazer a couple of weeks ago. And that works pretty well. I think that this new package I found might work even a little bit better. And notice, I'm still learning some of this stuff too. Like, I'm trying to figure out the best way to do it. This model summary package is new. A friend and alum of the doc program recommended it to me. So I'm going to load this in. And if you don't have it, you can install it, of course, under here and just type model summary. And then I'm going to use the package called broom.mixed. And Broom is, again, a tidyverse package that is used to clean up estimates and put them in tidy formats. So Broom.mixed is just a package that is used to do the same thing for linear mixed models, so like LME4. So we're going to load both of those. And now I'm going to build that list. Remember before I created an empty list? Well, now I'm actually going to fill it out. And in that list, I'm going to list the models in the order I want them to appear on the table, in my fancy table. So I've got list, so models is equal to a list. And then in paren, I have model.0, comma, model.1, 2, 3, 4, and 5. And I don't need to put quotes or anything around these because these are already objects that are defined in my environment. So I'm going to run just that line. Oh, model.4 is not defined. Oh, wow. Let me go up and see if I can run. Yeah, I didn't actually run model.4. I must have talked about it, but not ran it. There we go. Now it should be in there. Yeah, there's model.4. Okay. Now let's try running it. There we go. So now when I look at models, models is a large list with 6 elements. And the 6 elements are my 6 models. So from there, I can just, now that I've loaded this package called model summary, I can just run model summary for models. And look at that, you get a really nice, clean summary of all the models. So here's model 1, 2, 3, 4, 5, 6. Oh, I wonder why I didn't call it model.0. That's interesting. So model 1 is actually my null model, 2, 3, 4, 5, and 6. And here are my estimates for my intercept. The standard errors are in parentheses. This line, this is the standard deviation of my random intercept. And this is the standard deviation of the individual level error term. That's a little tricky because it's usually a variance. So you could square that if you wanted, or you could just report the standard deviation there. That's fine. Then I have my estimates for t-sig and their standard errors, my estimates for lead, and then this is my interaction. So we can kind of follow the model as it builds from 1, 2, 3, 4, 5, 6. So this is the kind of table that you would find for publication. This is a summary table of all the models we've built. And then we also have AIC, BIC, and log likelihood along the way too, which is really, really cool. And if you want to go a step further, you can actually output this. So this looks really nice in the HTML notebook that we have, but you can go a step further. You can actually output this. So here I'm just running the command again, and I'm adding an option, output equals msum.html. So this is actually going to make an HTML file. And then I'm going to give it a name at the top called MLM estimates. So I'm going to run this. I don't know why I get a weird error down here, but this does seem to work. And then if I go back to my files, to my working directory, and I click refresh, I should have a new file down here called msum.html. Now you may not have the doc yet, that's from me practicing earlier, but you should have a document or a file called msum.html. Now here's the cool thing. Let me minimize out of here. If you go into Microsoft Word, you can open, let me close this, you can actually open HTML files within Microsoft Word. So here it is for me, it's right at the top. This is my same folder that I was in week 4. And Word will see, recognize, and open HTML files. So essentially, it's taken your model, and now it's in a Word format. So you now essentially have a Word table. And you can clean this up a little bit, so you can click on this sign, you can highlight everything. I really like, well, first of all, I want to switch this from web view to page view. So there are all 6 models. That looks great. You can make everything black to get everything lined up. And there you have a really nice summary of all the models all on one page, and you don't have to sit there and type in all the values. And it's very easy to APA-ize this, right? So you can, you can put lines at the bottom and top, put lines here. Of course, I don't have to show you how to APA-ize a table, I'm sure. That's something you all have done a time or two before. But it's very well suited to creating a nice Word version summary. And then to save this, you can just go to Save As and just save it not as a web page, but as a Word doc, like that. And in this case, I'm going to overwrite the one I already have. So in a matter of seconds, you've gone from the raw work in R to a table that you can publish, which is really cool. And in later weeks, I'm going to show you how to make a descriptives table in the same way, so you don't have to spend a ton of time making descriptives either. All right. Okay, I think I've covered everything this week. Just to recap, in part 2, we talked about how to run multi-level models in R using the LME4 package. Again, I recommend naming each model so that you save it to memory and can come back to it. We calculated an ICC. We talked about adding variables sequentially, adding interaction terms, and then testing the significance of those things using the ANOVA command to compare 2 nested models. One bummer about R, we don't get p-values, but as long as we keep in mind the cutoff values for a t-statistic, -2, below -2, or above +2 is kind of the bare minimum, we can at least get a sense of how significant these things are. And then of course we get a true p-value by running this ANOVA command. And then we made a cool summary table and something we can work with in Word. All right, hopefully that makes sense. I hope you have a great week, and I will talk to you soon.